So today we're looking at limits again, but now we're going to look at algebraically or an analytical value of a limit. And for most people, the algebraic and the analytical portion of limits makes a lot more sense than the graphical or the numeric or looking at that chart. All of them are important because it gives you a fundamental idea of what a limit looks like, but the algebraic is more of the way kind of we think, just because we've done a lot of algebra so far in our mathematical career. So I like to say the first rule of limits. And as we get into note cards, we'll start making these things make a little more sense. But the first rule of limits, my first rule of limits, is always the plug and chug. And what does that mean? It means plug the value in, the x value. If you get a value out, then that's generally going to be the value or the limiting value of the function, unless we have a piecewise function. But if we're just looking at a polynomial type function, if we plug the value in, the limit in, we get a value out, the value is going to equal the limit. And we're done. If it doesn't, or if we get something else, which we'll talk about, then we got to do some other things with it. And that's where the algebra comes in at. Algebra, factoring. Oh, yes, yes, yes. So, example 1 here. Limit as x goes to 1 of 2x squared minus 3x plus 1. So if I were to take that 1, here's where my plugging and chugging comes in. If I plug in 1 for my x values, I know that I get 2 times 1 squared minus 3 times 1 plus 1. Well, 2 times 1 squared gives me 2, minus 3 plus 1. 2 minus 3 is negative 1, plus 1 gives me 0. So I know that this function is defined when x equals 1. I also know, more importantly, that 2x squared minus 3x plus 1 is a parabolic function opening up. So I know that this function is defined everywhere on that graph. So the limit as x approaches 1 is that value of 0. So my limit is my value. Likewise, in example 2, I know the absolute value of x minus 1 is going to be a v. So I know that it's defined along all of those points. For every x value, I can get a y value out. So if I plug in 0 for x, I get the absolute value of 0 minus 1. Absolute value of 0 minus 1. 0 minus 1 is negative 1. So the absolute value of negative 1 gives me 1. So the limit as x approaches 0 is 1. So again, through plugging and chugging, I know the value is equal to the limit. And that's going to be the first thing we're going to look for. So example 3. Notice we got a nice clean sheet of paper, so it's going to be a little more interesting, huh? So limit as x goes to 1 of x squared minus 3x plus 2 over x minus 1. So here, if I plug in 1, do the plugging and chugging, we get 1 squared minus 3 times 1 plus 2 over 1 minus 1. That in your mind should trigger, uh-oh, we've got issues. Well, we're continuing here. We get 1 minus 3 plus 2 over 0. 1 minus 3 plus 2 gives us 0 over 0. Very important that we see that 0 over 0. We know we can't divide by 0. And 0 divided by 0 is not possible. We call this the indeterminate form. If I can spell today. So indeterminate, that is not even close. Indeterminate form. So whenever we get 0 over 0, we know we've got to do something in order to be able to find the limit. Well, what is that something? And this is going to lead us to our first theorem. And this theorem is the longest, I do believe, name for a theorem. It's the functions that agree at all but one point theorem. Well, what does that mean? Well, what does it say? It says that if f of x equals g of x, for all x values except at one point, so they agree at all but one point, we call it value c, then a limit, and the limit of g of x exists, then a limit of f of x is also going to exist such that the limit as x goes to c of f of x equals the limit as x goes to c of g of x. That's a mouthful. What does that mean? Well, as always, I will kind of give you a graphical representation so you can kind of visualize what that means. So we have a function. We have f of x. So maybe f of x comes in like this. We're going to put c in here. And then we're going to come out like this maybe. And then maybe what happens with g of x, maybe g of x comes in the same. They exist, and this is our f of x. They're the same exact graph except at c. So maybe we come across here, and then maybe g of x, there's a hole, and maybe g of x is defined up here maybe. So now what we have is this graph, and this graph f of x, and then this one was our g of x, which was the same function, but we jumped over here for the value, and then we came back down. So these two graphs are exactly the same, except here at c. Well, I know then that the limit, if I know the limit of f of x is going to be whatever value this is, we'll call it f of c, then we know the limit of g of x is also going to be, we'll call it f of c, we'll call it L. So we know the limit of f of x is L. We also know the limit of g of x is L, because these two branches are coming to the same exact value. Not that the two values are the same as x gets closer to c, but the branches get closer to that same value of L. So how does that play into the limits of these functions? Well, notice, there's our friend that we just talked about. We're going to talk about two techniques today. The first one is the dividing out or the factoring technique. So as I plug in my 1, notice again, we ended up with 0 over 0, which is indeterminate. So we're going to do something with it. So in this case, we're going to factor. So if I factor, I end up with x minus 2 times x minus 1 over x minus 1. So we have the limit as x approaches 1 of that function. Notice we can factor, we can cancel out that x minus 1, and we get the function x minus 2. So we're looking at the limit as x approaches 1 of x minus 2. So we've now created a different function. X minus 2 is not the same function as this up here, but these two functions look very similar to each other if we were to graph them. If you put them into your calculator, you're going to notice that x minus 2 is going to be a linear function. We're going to go through that 2 there. It's going to come up. As we get closer and closer to 1, we're going to see that we have just a nice linear function. But if I look at this function, this rational function, I know that as x gets closer to 1, it is undefined. We have a hole there at negative 1. So my two functions here, we could call this f of x if you want, and we call this g of x if you want. So I know that these two functions agree with each other because they're exact same graph, except at that one point. Again, we could throw this into the calculator. Go to y equals. We're going to clear that out. So we're going to type in x minus 2. We're going to type in, again, the numerator in parentheses, x squared minus 3x plus 2 divided by the x minus 1. Not in parentheses yet. And as I graph that, we should probably change our windows. Remember, oh, come on. Change our windows there. We're interested in at x value of 1 there. So let's go from, let's say, negative 5 to 5. Now, if I were to graph them, here comes my first function. It's graphed. And now comes in my second function. And notice it looks like it's full. However, if I were to type in -1, so if I hit trace and I go to -1 by typing in typing in 1, in y1, that value is defined, -1, which makes sense because it's a linear function. But if I go up to y2 and I type in that 1, notice we don't get a value out. So these two graphs are going to agree all but at one point. So you can type in any other number there. X equals 5. For y2 we get 3. And here at y1 we get 3. Type in 7. No, we can't type in 7. We only went from -5 to 5. Type in -3. We get -5. If I jump up to y2, -3, I get -5. So we should, hopefully, with all the functions that we've worked with, notice that these agree at all but one point. So what does that tell me? Well, it tells me that if I know the limit of g of x, I also know the limit of f of x. So if I look at the limit as x approaches 1 of x minus 2, again, plug and chug. If I plug in 1, I get -1. That limit is actually the limit of this function up here as well. So the limit of x squared minus 3x plus 2 over x minus 1 is -1. Likewise, g of x minus 2 is -1. We can do this as long as we can factor. So with this one, example 4, if I go to x -2 of x to the third plus 8 over x plus 2. Again, I'm going to plug -2 in to see what happens. -2 to the third is -8, plus 8 gives me 0. -2 plus 2 gives me 0, so 0 of 0, again, indeterminate. So that tells me that I got to do something with it. Again, we're going to look at the factoring or the dividing out portion. So how does x to the third plus 8 factor? Yes, cubics. So again, the x to the third plus 8 goes to x plus 2. Remember, we take the cube root of each of those terms, x plus x and 2. We're going to square that first term of our binomial. We're going to multiply those two together and change the sign. And then we're going to multiply the last one to itself. And that's going to be over our x plus 2. Our x plus 2's will cancel, so there's my whole that we saw up here. So I'm now looking at x squared minus 2x plus 4. So if I take the limit as x approaches 2 of x squared minus 2x plus 4, if I get a value out of that, then I know the limit of my original function. If I plug in -2, I end up with 4 plus 4 plus 4, or 12. So the limit of this is defined as 12. We know also the limit up here is going to be 12 because these two graphs agree at all but one point using our theorem. The next method I want to talk about is the rationalizing or the conjugating method. So there was a reason that we rationalized denominators back in Algebra 2 and in pre-calculus, and that is to help us with some of our limits. We take the limit as x approaches 9 of x minus 9 over the square root of x minus 3. If I plug in 9, again I get 0. And if I plug in 9 here, I get the square root of 9 minus 3 gives me 0. So again, we know that that is indeterminate. I don't know why I keep putting a T there. Indeterminate. So what does that tell me to do? Well, I got to factor. Can we factor x minus 9? And yes, actually we can. I know we told you back in Algebra 2 you can't. But x minus 9 does factor. If you want, remember we multiply those first two terms, got to give us x. So if I take the square root of x times the square root of x, that gives us x. -9, I can break up into -3 and +3. So the square root of x minus 3 and the square root of x plus 3 multiplied together gives me x minus 9. Well, that there then allows us to cancel out the square root of x minus 3's, leaves us the square root of x plus 3. So I can take the limit as x approaches 9 of the square root of x plus 3. Plugging in 9, I get square root of 9, which is 3, plus 3 gives me 6. So we know that that function is going to go to 6. Now I also want to show you how to rationalize this, just because it makes it easier later on with some of our more complicated problems. But if you want to factor this, by all means, factor yourself to your heart's content. So how do we conjugate? Remember, to conjugate, we're going to take the x minus 9 over the square root of x minus 3, and we're going to multiply by the square root of x plus 3. So we want to make this the difference of squares eventually. So I'm going to leave the numerator as x minus 9 and the square root of x plus 3. But I'm going to multiply out my denominator. I'm going to multiply my conjugates out. So if I multiply the square root of x minus 3 to the square root of x plus 3, I get x minus 9. So those values, those factors will cancel. So I'm looking at the square root of x plus 3, which we just looked at previously. The limit as x goes to 9 of the square root of x plus 3 gives me 6. So again, either way you look at it, we all get the same answer of 6. Sometimes, though, factoring just does not work for us. So in example 6, if I take the square root of x plus 9 minus 3 over x, and I ask you to factor the x, that's going to be almost nearly impossible for us to know what the factors are. But we could conjugate. Well, first I guess we should plug in the 0 and see what happens. If I plug in 0, I end up with 0 over 0, which is indeterminate. So that tells me I gotta do something else with it. So I'm going to conjugate, in this case, the numerator. So the conjugate of the numerator is the square root of x plus 9 plus 3. And I'm going to multiply that on the denominator as well. Again, I'm going to multiply my two conjugates together, leaving my non-conjugates by themselves. So if here I take the square root of x plus 9 to the square root of x plus 9, I get x plus 9. My negative 3 radical and my positive 3 radical are going to cancel each other out, just like any conjugates do. And then I get negative 3 times 3 gives me a negative 9. And that's over our x times the square root of x plus 9 plus 3. My numerator simplifies to just x. 9 minus 9 gives us 0. So now my x's are going to cancel. So I have 1 over the square root of x plus 9 plus 3. So now I can take the limit as x approaches 0 of 1 over the square root of x plus 9 plus 3. Now if I plug in my 0, I end up with 1 over 0 plus 9 gives me 9. Square root of 9 is 3. Plus 3 gives me 6. So I end up with a limit as x approaches 0 of 1/6. So the limit up here is actually going to be 1/6. Finally today, I know it's a long day, but I want to talk about the rules, some rules of limits. And these are pretty standard and pretty self-explanatory, I think. But I do want to go through them. Just because we do see them on an AP exam and on multiple choice tests that I'll give you out shortly. So scalar multiplication. If I take the limit as x approaches some value of a number times a function, I can take that number and pull it out to the outside. That number has no bearing on the limit of the function itself. So I can write that as the constant, or that multiple times the limit as x goes to c of f of x. Remembering, only the x is changing. So I can't pull an x out, but I can pull a constant out if I'm multiplying it through. I can break up the sum and difference of limits. So if I take the limit as x goes to c of a function plus or minus another function, I can separate it to two different limits and add or subtract them from each other. The quotient, I can take the limit as x goes to c of f of x over g of x. And that's equal to the limit of the numerator's limit divided by the limit of the denominator. Same thing with product. If I'm multiplying two functions together, I can split those two limits up and then find the product of those. A power, if I have a function to an exponent, I can take the limit of the function and then take that value to an exponent. And then a constant. The limit of any constant is that constant. So graphically, if we have a constant, that would be our function, or in this case is our b. So it doesn't matter where our c value is. C can be over here if we want. That value is always going to be that same b value. So how do we see kind of these problems occurring in our lesson? Well, they're going to give us some information. They're going to tell us, in this case, example 6, the limit as x goes to c of f of x is 4, and of g of x, it's -1. So can we find the limit as x goes to c of f of x times g of x? So if you want to write this out, you can, but hopefully, again, it's intuitive. I can write this as the limit as x goes to c of f of x times the limit as x goes to c of g of x. I know this limit. They tell us it's 4. I know this limit. They tell us it's -1. So 4 times -1 gives us -4. So the limit up here would be -4 as well. Again, with example 7, we know the limit of a function to an exponent. So I could find the limit of the function and then take it to that exponent. So the limit of f of x is 4. So I'm going to take 4 and square it. It's going to give me 16. Finally, I've got a scalar multiplier and a quotient. So I can break this up into 3 times the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. So that gives us 3 times, we know this limit, again, is 4. We know this limit is -1. So 3 times -4 gives us -12. And hopefully those are some intuitive rules of limits, but important nonetheless. Happy limiting!